or which one do you want to work? Not which one. Drawing the circuit. So all we're going to do is just draw the Zener portion of the circuit. We're not going to draw all the transformers and the regulators and the filters and all that stuff. We're just going to draw the regulation portion of the circuit, kind of like we did on the lab. So all the circuits will look the same, guys. The only thing that's going to change is just the parameters of the circuit. So we'll start off by coming in and we'll draw RS. And then we'll figure out if it's a negative supply or a positive supply. This looks like it's a positive supply. So this is unregulated in right here, unregulated filter. DC. We're going to call this RS, but in real life you'll understand it's not going to be RS. We just use it for formula. To figure out a formula. In real life it'll be R10 or R15 or whatever it's supposed to be. Since this is a positive regulator, we'll draw, so the Zener split into a circuit reverse bias. And then we'll come over here and this is going to be out. This is going to be regulated, of course. So my Zener is going to be an 8.2 volt Zener. Y'all see where I got that. Right here where it says regulated output is equal to 8.2 volts. And we'll figure out, we'll have to look that up and figure out what it's going to be. Does it ask you that? Is that on the worksheet? Is y'all supposed to figure out what Zener we're going to use? Okay, so don't ask you what Zener it is, right? I mean, on the very first part of the lab, when it gives you the overall instruction. Okay, so what I did is I think somebody in the class actually brought this up, is that the data sheets were not up there. So that was one of the things that I did doing this morning as I was up and uploading the data sheets, so you can have them at home. Of course, here, what you'll do is you'll just come over and get one of our reference books. But if you got your computer and you want to look it up just to see if they're there, that might be a good idea too, because once you draw them up, you have to make them visible and all kind of stuff. So what I see is not exactly what you see. So ETC. Oops. And so inside the course material, course content, then we have a folder in here referred to as data sheet. In fact, let me switch over to your view to make sure I'm seeing what you see. And there's a worksheet right there in the back. So course content, data sheets, and then 1N47 Zeners. I'm going to try to come in up here and arrange them according to grade, because right now they're arranged in the data sheet folder alphabetically, and I want to try to get them together so you'll see that, like so diodes, Zeners, stuff like that. So this is what we're looking at. And of course, if you don't have your computer up, then you probably need to come over and get one of these data books, right? But this will give you access to it from the house. And we're looking for an 8.1 volt Zener. So we'll come down the Zeners. It says 8.1. So what it says, 8.1? I might have to change it because I don't see 8.1 on here. 8.2, good, thank you. 8.2, I think I thought I'd missed that. So the 8.2 volt Zener, we come down to Zener volts, 8.2, so we're going to use the 1 in 4738. And A, I guess, because it doesn't say that. It say plus or minus 5%, or it say plus or minus 10% on the worksheet. Okay, so 1 in 4738. So the A would be 5%. And then if it don't have the A, it's a 10%. And of course, the other thing that we need off here, of course, we know these are all 1 watt Zeners. So the only other thing we need out of this is IZK. So IZK for the 1 in 47. For IZK is, can't see the data sheet. IZK 500 micrograms. 500 micrograms, right? Okay, so far. So you'll need to write that information down, probably on your worksheet. So we know this is 8 volts plus or minus 10%. And we know IZK is equal to 500 micrograms. Okay. Well, this will be the drawing. Make real simple. Of course, I'm going to put values in for RS up here once we calculate what it's supposed to be. Okay. So the next thing I'll do is I'll figure out my unregulated N. So Vn maximum would equal to 12.4 times 1.1. So equal that, you'll understand that. What we're doing is doing the 10% without doing the 10 and then add and subtract it. Y'all understand that? Yes or no? So if I want to increase them, so back in DC, the way you learn how to do percentage is I'd take the 12.4, I'd multiply it by 0.1, and then what would that come up to give it? What's that? And then I would come up here and I'd take my 12.4, and then I would add 1.24 to it, and then I would take my 12.4 and I subtract 1.24 from it, kind of like you did in DC when you were calculating your resistor values, right? So what do we come up when we go through this one right here? $12.4 plus 1.24. So what we got? 13.8. Okay, 64. Or 13.6. Well, let's take 12.4 and multiply it by 1.1. So this is what we're saying. So what you can do on your percentages, so I can say D in max, D in minimum, would be equal to 12.4 times 0.9. So all I'm doing is subtracting 10 from. So this is just a trick that I learned. And what it does is it saves you one math operation. But either way, if you want to do it this way, if you want to do it the way you learned at DC, is to multiply it times the percentage, come up with a value, add it to it, and subtract it from it. That is fine. What do we come up with here if I take it and I subtract 1.24 from this? You're listening. Or we can multiply by a point. Huh? 11.2. 16. Now we're rounding to one decimal point. Because everything we do in here is an approximation. Nothing we calculate is going to come up exactly right. Y'all understand that? So in here what we're doing is we're just rounding to one decimal. So 11.16. If you want to keep 11.16, then that's fine. You know, it's just that you'll come up with a close answer, and if we do 11.2, we'll come up with a close answer. We won't come up right, right? 13.6. I thought it was 6.4. I thought it was 13.64. Well, 4 rounds down. 5 and above rounds up, right? For 5%. Yeah, but this is 10%. For 10, yeah, so what I do on the top one is I just put the percentage on the other side of what? On the other side of 1 of a fraction. Yeah, for the other one I just subtract it. So we should have came up with the same answer right here. So I learned that a long time ago instead of going through 2 math operations. So every math operation you do, there's a chance of having an error, right? So it's up to you. You can do it this way. Then I need to calculate the voltage drop across RS, and this is the mistake that we've been making. We've been using this guy and screwing up instead of using the voltage drop across RS. So VRS, the maximum, would be what's on this side. It would be the maximum voltage, 13.6, minus this right here. So we're using what law? We're using Kirchhoff's law. That says the voltage in a series loop has to equal to the defined voltage. So we know this is dropping 8.2. So this guy right here is going to drop whatever's left, right? You all understand? So this is going to be 13.6 minus 8.2. So the maximum voltage that resistor should ever have to drop would be whatever I come up with here. So what we got? 5.4. Then VRS minimum, I'll take the minimum input voltage. So what's nice is the Zener is going to give us the same voltage. So this is the minimum. This is going to be 11.2 minus 8.2. What does that give me? Yeah, 3. Good. So is everybody okay so far? Just making room. That's V out. That's V out. It's just the way we say it, right? V out. So whatever's across the Zener is V out. Because the load is in parallel with the Zener. The Zener's trying to maintain a constant load, voltage. So no matter what I hook up out here, whether it's a light bulb, whether it's a resistor, whether it's some type of solid state device, I'm designing it around this current, and I'm designing it around this voltage. Okay, so we've got everything we need. We got IZK, we got the Zener voltage, and we need to calculate RS. Now, what we need to do, and this is the kind of questions that I think on the topic quiz for Zeners, is what's going on with the Zener? Well, that Zener automatically changes its opposition to try to maintain that 8.2 volts within 10%. So if my load current is 100 milliamps, okay, and then my input voltage goes up, that resistor drops more voltage. According to Kirchhoff's current law, the sums of the current flows in these two branches right here has always got to equal the total current. Well, the total current is flowing through RS. So if the input voltage goes up and the load current doesn't change, then what's the Zener got to do? Is it going to conduct more current or is it going to conduct less current? Huh? It's going to conduct more because the input voltage goes up. I have 8.2 volts over here. The input voltage goes up. That means RS has got to drop more voltage. Well, how does it drop more voltage? It's got to conduct more current, right? You understand that? But the sums of the current, it's got to be the Zener takes the total current minus 100 milliamps. Well, if the total current goes up and the load current doesn't change, then the Zener current's got to do what? It's got to go up. If the input voltage goes down, then Zener current goes down. If the load current goes up and the input voltage don't change, so let's say the load current goes up to 150 millivolts, but the input voltage don't change. Well, if the input voltage don't change, if the input voltage, what did I say? If the input voltage don't change, that means the voltage drop across RS doesn't change. If the input current goes up, then the Zener current's got to go down. Y'all understand that? So that Zener current, so it's literally changing its dynamic resistance. So this is the big change between solid state devices and resistors. We can set up these things so they dynamically change their opposition. And bipolar transistors are exactly right. So if I'm going to calculate that resistor, I need to make sure, and we're trying to keep this thing operating above what we call above the knee, but that's not looking right. We got to operate it at a current that's above the knee. So I'm gonna do everything I can to make that thing operate up in here. So this is IZK, and this is IZ max. I want it to operate somewhere in here. So when I choose that resistor, I want to move it this way. I don't want to move it that way, right? You understand that? So that's why if minimum current, if voltage goes down, Zener current goes down, which will move it which way? So what I want to do is I want to make sure I have enough current to get out of that knee. So that's why I'm going to use VRS minimum. When this current goes up, Zener current goes down. I want to move it this way, right? You understand? So that's why we're going to use out of the load maximum, which will put it right here, and then I'm going to put plus IZK, so we got at least knee current flowing, and that's why we solve for RS. So what's my minimum voltage? 3 volts. What's my maximum current? 150, and then plus 500 microamps. So here's Caesar 0.5 milli. So the math is a little easier. So that's going to be 3. So RS calculated is going to be what? It's going to be 3 divided by 150.5 million. Is that right? Yeah, what I did is I went ahead and converted it to milli. So 500 micro is the same as 0.5 milli. Okay. So this is 105 milli. So what size are we going to choose for RS? So this is the calculated. What are we calculating for RS? Huh? Same over 20. That's okay. Okay, so what am I going to do with the 20 ohms? Am I going to use 20 ohms? No. 20 ohms would put it right here. That's where 20 ohms would put it. If we was operating at the maximum voltage and minimum current, I want to move away from that. I want to make sure I'm getting away from that IZK. Okay. So what we just calculated was if I have the minimum voltage and the maximum current, this guy would operate at IZK. I'm right at the hairy edge of getting out of regulation. So this resistor, we always round down. We always go to the next standard. So what do we choose? 18. And then I check the tolerance. And then we'd say times 1.05. So it's pretty easy on this one to figure out what you're going to use, because if it's 10%, you use 1.1, right? If it's 20%, you use 1.2. If it's a 4% resistor, you use 1.04. And that saves you a math operation. So what does this come up and give me? So 20 ohms is perfect, right? It'll have to be a plus or minus 5%, right? Okay, so what else do I need to do once I calculate the size of the resistor? So what's the three things the resistors are rated? This is going to be on the next step. What's the ohm? Okay, well, power, wattage, ohm. Well, we know power, wattage is the same thing. You got me confused. Tolerance, thank you. Well, we got the tolerance, we got the ohm, so we got to make sure we're not going to burn this thing up, right? So when would the current through the resistor be maximum? When it's dropping its maximum voltage. So that's when the current in the circuit will be maximum, right? So power of the resistor, PR, be equal to, what's the maximum voltage it's going to drop? 5.4 squared divided by 20 ohms. Or you could calculate the current. So you could do that one. Or you could say IR max, what you learned in DC, would be equal to 5.4 divided by 20 ohms. And then you could take PR, would be equal to IR max times max. So you can do it with two formulas, or you can do it with one. Oh, I'm sorry. Because I looked down here and saw that. And I was seeing if you paying attention. Isn't that what most instructors say? When they make mistakes. So that's good, thank you. Because I glanced down at my, of course that's 19. And this would be, okay, so you make, we're choosing the resistor that we chose, not the resistor that we calculated. If I need to pay closer attention. So we chose an 18. Thank you. Really? P square over R. Huh? You did 15 squared again. Yeah, I know. Yeah. So what would, so we calculated PR and we calculated what? Yeah, but what did we come up with? So it means we would have to use at least a 2 watt resistor. Okay, what's the power of the, dissipated by the Zener? What's the maximum power dissipated by the Zener? So here we will use this formula right here. PRZ, we're going to use GZ, rich, times IZ maximum. So how are we going to come up with VZ? So we know VC is pretty easy. So PRZ, because it's given, is going to be equal to 8.2 times what current? When would the current flow through the Zener be maximum? No, the 5.4 divided by 18 would give us the maximum current that flows through the resistor. Then I would have to come back and I would multiply that by the voltage, the maximum voltage that the resistor drops to come up and get the power. So back in DC, this is the way you learn how to calculate power. But we actually know we got 3 formulas we can calculate power with, right? What are the 3 formulas that you need to know? Well, first of all, the main formula is P is equal to V times I, right? Yeah, this is I squared R, and then power is also equal to V squared up here, Rich, R. So what's nice about this is that if you know those 3 formulas, you can always go back to this, but it takes more math, right, to understand. So what I did up here is I said, okay, IR max would equal to 5.4 divided by 18. That's the size of the resistor. That's the maximum voltage it's going to drop divided by the size of the resistor. Yeah, I need to make that clear. And hopefully my 10 comes up and still works, so that's going to be awful. Okay, started working here. What I'm about to do is I'm going to, since it didn't cut, I saved this. So that means I can't change it. So we got 3 power formulas. We got power is equal to V times I. Then we got power is equal to I squared R. And we got power is equal to V squared divided by R. So there's our 3 main power formulas. And they all came from this one, guys. I don't know if DC showed y'all that. So this is the one most people want to use right here. P is equal to I times D, or V times I. You know, you can swap that around. But the problem is that to calculate the maximum power of the resistor, we need to know the maximum current that flows through it. So what I did up here is I said 5.4 divided by 18. That gives me my maximum current. And then I multiply that times the maximum voltage, and that would give me power. Or, to save a math operation, I could use the maximum voltage it's going to drop, which is 5.4 squared divided by R. And we should come up and get the same answer. Now, what's nice about knowing these other power formulas is most of the time it's going to save you one math operation. Either way, you should come up and get the same answer. Whichever way you want to do it, you should get the same answer. So most of the time we can get back to that formula right there. It's just that if it's not in that format, then I've got to make one more calculation to come up and get it in that format.
So in the IR, so 5.4 divided by 18.
Yeah, that gives me the maximum current, and you can't. That says IR max.
And that would be 5.4.
The maximum current, not the maximum current. So the maximum current that is going to flow through that resistor is when it's dropping its maximum voltage. Right? You understand? So what I did is this number right here came from here, because I'm trying to calculate the maximum current, right? And then we divide it by the size of the resistor. So R is equal to what? V over R. That makes sense. So this is the resistor that we chose. So that goes right here. And then, so this formula works. Or I could use this formula right here where it's equal to V squared over R. I take the maximum voltage that it's going to drop, so that's when the power would be, and then I square that, and then I divide it by the size of the resistor. And you should come up with the same value. It depends on how you run. Does that make sense? Well, what we're trying to do is we're trying to calculate when the current flow through the Zener is maximum. So if the load current goes up, Zener current goes down. If load current goes down, Zener current goes up. So what we're going to do is we're going to say, okay, what's the current flow through the Zener? Well, the current flow, and I'm going to use conventional current because it just makes it easier to see. So here comes the input current. And then our input current divides in 2 directions. It divides here and it divides to the load. So we know Zener current, so this is IZ. We know that Zener current goes down. We know that Zener current goes down when the load current goes up. And we know Zener current goes up when the load current goes down. So what I'm trying to do is figure out what is the maximum current that would ever flow through RS? So we've already calculated it. So here's the maximum current that would ever flow through RS. So what is that? Anybody calculate this? So IRS maximum would be when it's dropping the maximum voltage. Oops, Rich. When it's dropping the maximum voltage. That's right, 5.4. Divided by the size of the resistor. So what's RS max? I'm looking at milliamps, yeah. 300 milliamps. So I know it's going to be times, I'm going to put 300 milliamps minus the minimum load current. And this will give us the current through the Zener. So right here we're using what? We're using Kirchhoff's current law. Because they're in parallel. So I know this current flow here. I don't know this current flow here, but I know the total current flow in the circuit. So this is Kirchhoff's current law we use right here. This is total current. Minus the minimum load current. Oh yeah, so total current, total I total is got to equal to IZ plus IL. It's always got to equal that, right? You understand that? So if this guy right here stays constant and this guy goes up, then this guy's got to go down. It's got to. Or vice versa, right? You understand that? So what we're trying to do is figure out when the Zener current is going to be maximum. So I know this, I know IT, I know IL. So the Zener current has got to be the difference, right? You'll understand, yes or no? So what's the power of my Zener? That's right. $300 milliliter, 5.4, it can't come up to be the same. Because one of them's dropping a maximum 5.4 volts, and the Zener's dropping 8.2 volts. Had a lower current. I guess it might, yeah, it might, yeah. So, can I use a 1N47, what did we come up with, 1N47? We didn't write the part number down, did I? Not an A, we're using just, it's plus minus 10%. One N 4738. So can I use a 1N 4738 for this circuit? Yes or no? Yes or no? Oh. I thought I had left with it. Hey. So can I use this Zener?
So, no.
No. Yeah. So that means I'd have to find a Zener that is at least 2 watts, right? We use this is, so the site that we buy a bunch of parts from, I really like it. It's called Jemeco, JEMECO.com. And you could come up here on the top and say like 1 watt. Like we can come up here and just say like Zener diode and just search. And then what it'll do is it'll show us their Zeners. And right off the bat, it'll give us 1 watt, 500 milliwatts, 1 watt, 1 watt. I don't know if let's see if they got one. 500 milliwatts, 500 milliwatts, 5 watts. There's a 5 watt Zener right there. And then when you come up here and click on it, then right here it says I can get the watt on it. I can get the data sheet. So I click on the data sheet, it comes in as a PDF, and I can get any data. So this gives me the whole line of 5443 Zeners. And these are all rated at what? 5 watts. So we chose a Zener that we were familiar with, but then we found out that if I used that Zener, I would do what? I would burn it up. But the problem is it would only burn it up at a certain situation. When the input voltage was maximum and the load current was minimum, it would burn it up. So that means I could design it, I could put it in there, and it might work for 2 weeks or 4 weeks, and all of a sudden it just burns up. Because we hit that what? We hit that maximum voltage and minimum current and burn it up. So Jemeco is a real good site. We like it because it's got almost every part that we use, but this is where almost all the data sheets that is on your website came from Jemeco. So that's circuit number 5, guys. And remember, on these worksheets, you're not graded on accuracy, you're graded on the attempt, right? Y'all understand that? So everybody's got credit for this.
What are you writing?
Oh, my PowerPoint? Yes. The mass confusion.
I was still writing down something.
So it's all over the place, Janice.
What I was looking at is one that's called the Kirchhoff law.
Yeah, well, we use Kirchhoff's law to calculate the current, right? We know that the Zener is the voltage across the Zener, right? Understand that. So that goes right here. Let me get a different color. So voltage across the Zener, that goes right here. And then the maximum current that we're going to get through the resistor goes right here. And then the minimum current of the load goes right there. Yeah, what we're trying to do is figure out when the current flow through the Zener is maximum. And we know the voltage that's given. And another reason why we'd make sure, even if this came up with exactly 1 watt, or even around 1 watt, we would go ahead and round it up, because that zener voltage is plus and minus 10%.